Aloha. Hypothesis testing has long been a cornerstone of classical statistics, yet it is not without its shortcomings. One significant concern is confirmation bias, a cognitive bias well documented in psychology. This bias refers to the tendency to interpret evidence in ways that affirm one's pre-existing beliefs or expectations. Well, everyone else is biased except me. I am the most objective scholar in the world. Just kidding. If I think so, then I am biased about my bias. In research, a researcher introducing a new treatment or theory often hopes to demonstrate its efficacy or validity. This bias may influence the design of a study and the collection of data, subtly skewing efforts toward supporting the alternate hypothesis, suggesting an effect or correctness, rather than the null hypothesis, suggesting no effect or falsity. This inclination can manifest in practices like p-hacking, where researchers conduct multiple statistical tests until a significant p-value emerges. As a result, many academic publications risk being inundated with questionable or irreproducible findings. Some people even called it junk science. What should be done? A widely recommended solution is to set aside preconceptions and avoid any actions that could bias results toward either the null or alternate hypothesis. While this is sound advice, it is often easier said than done. A more proactive approach involves deliberately seeking counter-evidence that challenges the initial finding or one's own beliefs. History provides examples of such rigorous inquiry. The discovery of X-rays is a striking case where a scientist believed in the null hypothesis before accepting the alternate hypothesis. In 1895, German physicist Wilhelm Röntgen observed a mysterious fluorescent glow while experimenting with a cathode ray tube. Further investigation revealed that this invisible light could pass through human flesh and other materials, producing an image of the bones in his hand. Rather than rushing to declare his discovery, Röntgen diligently worked to negate it. His null hypothesis posited that no invisible light capable of penetrating tissues and metals existed. Röntgen conducted X-ray experiments on his wife, Anna Bertha Röntgen. He asked his wife to place her left hand on a photographic plate for 15 minutes while he exposed it to X-rays. The resulting image, known as hand with rings, showed the bones of her hand and the wedding ring. When Anna Bertha saw the image of her skeletal hand, she exclaimed, "I have seen my death." Perhaps a more fitting reaction would have been, "I want a divorce from this mad scientist." Through careful experimentation and successful replication by others, the alternate hypothesis was ultimately confirmed. This disciplined approach lends greater credibility to conclusions. By striving to falsify his findings rather than seeking personal validation, Röntgen ensured the robustness of his discovery. His example underscores the value of adopting a mindset that prioritizes falsification over affirmation, even when the latter might align with one's interests or aspirations. The cautious approach to the study of cosmic microwave background radiation is another good example. In 1964, Bell Labs engineers Arno Penzias and Robert Wilson made what would become one of the most significant discoveries in modern cosmology: the cosmic microwave background radiation. However, they approached their findings with exceptional caution and thoroughness before announcing them. Initially, Penzias and Wilson detected a persistent, low-level noise in their radio antenna that defied explanation. They meticulously examined every possible source of interference, even going so far as to remove pigeons nesting in the antenna and cleaning out their droppings, suspecting these might be causing the anomaly. Their skepticism led them to carefully rule out any local sources of noise or equipment malfunctions. After exhausting potential local explanations, they concluded the noise originated from outside our galaxy, though they were unaware of any known cosmic source that could account for it. A critical turning point came when Penzias discussed the puzzling signal with his friend Bernard F. Burke, an MIT professor. Burke informed Penzias of theoretical work predicting the existence of cosmic background radiation. Realizing the potential significance of their observations, Penzias reached out to Robert Dicke at Princeton University, whose team had been working on the theoretical implications of such radiation. Dicke and his team visited Bell Labs to assess the antenna and confirm the findings. To ensure scientific integrity and avoid conflict, they agreed to publish their results jointly. 2 papers were subsequently submitted to the Astrophysical Journal Letters, one by Dicke's team explaining the theoretical importance of the radiation, and the other by Penzias and Wilson detailing their measurements. Penzias and Wilson's thorough, cautious approach exemplifies scientific rigor at its finest. Rather than rushing to announce a groundbreaking discovery, they methodically verified their data, sought alternative explanations, and consulted experts in the field. This deliberate process of verification and collaboration not only lent credibility to their findings, but also contributed to a discovery that provided compelling evidence for the Big Bang theory and transformed our understanding of the universe. In contrast, the case of cold fusion in 1989 is an infamous example of premature scientific announcements and the subsequent fallout. Cold fusion refers to the possibility of achieving nuclear fusion, an energy-producing reaction that powers the sun and stars, at room temperature, rather than the extreme conditions of heat and pressure typically required. If successful, it promised a near-limitless, clean energy source. The saga began in March 1989 when 2 chemists, Martin Fleischmann and Stanley Pons from the University of Utah, announced they had achieved cold fusion using a simple tabletop experiment. They claimed their process produced excess heat, far more than could be accounted for by chemical reactions, along with nuclear byproducts like neutrons and tritium, which are hallmarks of fusion reactions. This move was partly driven by a desire to secure patents and funding, as well as to preempt rival researchers. The sensational nature of the claim captured global attention, raising hopes for a revolutionary new energy source. However, later numerous independent laboratories failed to reproduce the results under similar conditions. Fleischmann and Pons faced severe professional criticism. The University of Utah, which had backed their claims, also suffered reputational damage. The case of cold fusion is a typical example of confirmation bias. Fleischmann and Pons's strong belief of cold fusion led them to look for the data that favor their theory, resulting in misinterpretation and wishful thinking. In conclusion, the contrasting examples of Röntgen's discovery of X-rays, Penzias and Wilson's study of cosmic microwave background radiation, and Fleischmann and Pons's announcement of cold fusion vividly illustrate the critical role of scientific rigor in research. These lessons underscore the importance of maintaining skepticism, seeking counter-evidence, and upholding rigorous standards in research. By adopting a mindset that values falsification over affirmation and prioritizes thoroughness over haste, scientists can contribute to the integrity of their disciplines and the advancement of reliable knowledge. Humans are inherently fallible, and even well-trained researchers are not immune to bias. The information presented in this video may also contain biases. While achieving complete freedom from bias is unrealistic, my hope is that this video raises your awareness of the issue and encourages you to consider integrating my suggestions into your research. Thank you.